I just want to point out that I have a cat wandering around at my feet who's not even our cat. We have our front door open and there's a cat that sort of owns the neighborhood and is wandering in here. So if you hear meowing, not even my cat. All right, hey guys, welcome back. I have to tell you, I just met with the other class and we had a little bit of technical difficulties with my markers trying out. So I've got a whole bunch of other ones to try here, but you have to let me know what's visible and what's not. I'm going to have to rush out at some point and get some new ones. All right, so our goal today is to start what's going to occupy us the rest of the semester. The last 4 days is all going to be about Chapter 8. And these, in Chapter 8, what we've got is a bunch of theorems. They're actually very cool theorems. Mathematicians love them a lot. And when you look at them from the right perspective, they're not just closely related, but in fact, you can come up with a framework in which they all become just special cases of one theorem. It's called Stokes' theorem. And that one general form of Stokes' theorem, I would like to be able to introduce to you guys sometime before we run out of days. But you know, our semester got a little compressed here, so if I can't, I can't. But I do want to show you each of these special cases that are, first of all, they came first, historically speaking, before the more general one, and they are the ones that all the physicists and engineers and so on actually use. So what they're going to be are theorems that link the line integrals and the surface integrals and so on that we've had, and all these theorems will say that one integral is equal to another integral, but it'll be mixing the integrals up of different dimensions. So that's where I want to begin, is just to clarify all these kinds of things that I'm going to say about dimensions. I've been stressing that stuff for you guys as the semester has gone by, so now's a good time to kind of review how all these things work. So let me spin this stuff around and we'll get started. Let's see, this should go like this. All right, so a couple of things to say. First of all, what does it mean to talk about the dimension of an object? There's a formal definition of a dimension, but one that I have stressed for you guys is that when we are discussing our geometric sets with equations and inequalities, so we're trying to describe them implicitly, the way that you get your dimension is equal to the number of variables. That means the number of coordinates minus the number of equations. That's kind of not always true, but anyway, for our purposes, that's good enough. So if you describe, for example, if you describe a set by saying that x squared plus y squared plus z squared is less than or equal to 1, that's not an equation. You haven't really limited, you haven't changed the dimension at all. You've merely limited the portion of space you're talking about. But you're inside three-dimensional space here, and you've got just a chunk of three-dimensional space. So this is three variables, no equations, that equals no equal signs. And so this is a three-dimensional set. We call this ball a three-dimensional set. And there's other three-dimensional sets, but they all tend to look like a chunk of three-dimensional space. If I had written down an equal sign where the inequality is, now you have still three variables, but one equation. So that's a two-dimensional set. That's a surface now. And of course, this particular surface is a sphere, but we've looked at a lot of other surfaces. We get a lot of surfaces by, well, typically by writing one equation and three unknowns. So like the cone that you had in the last exam. If you write down two equations involving the three unknowns, or one equation and two unknowns, then that cuts down the dimension by one more, and as you guys know, that describes a curve. So this is the intersection of that sphere with a plane through the origin. And so that would be, in this case, that would be a great circle on the surface of the sphere. I haven't made too much of a big deal about it, but if you write down three equations and three unknowns, or two equations and two unknowns, or anything like that, then, well, then the number of dimensions of the resulting set would be 3 minus 3, which is 0, and a zero-dimensional set just means a finite number of points. In this case, I guess x and z would be the same, and y would be their negative, so this would be 3 times whatever the square is, so each one of the, so x would be like 1 over root 3, y is negative 1 over root 3, and z is 1 over root 3, or the negative of that combination. So this would be a set of just 2 points. So that's what a zero-dimensional set looks like: one-dimensional, two-dimensional, and three-dimensional. Okay, and we've used that idea of what dimension is all about, how you measure dimensions. We've done that a lot during the semester. Corresponding to each one of these things, we've got a notion of integration. The notion of integration always says, take your chunk of space, your surface curve points, split them up into pieces, multiply the value of some function on each piece, somewhere on each piece, and you multiply it by the notion of the size of your piece. Well, I know how to measure the size of a three-dimensional set. This is where we talk about volume elements. That's measuring that you multiply the value of a function times the volume of a little chunk. For the two-dimensional surfaces, I've used dA, the book uses ds, but this is always a reference to the area of your piece. For curves, I write dl, the book tends to write d little s. Even back in Calc 1, you had notion of a dx, which stood for the length of a little piece of the x-axis. But all of those were measurements of lengths. And in the case of a zero-dimensional set, I don't know what I would use. The way that I would measure the size of a finite set, I guess, would just be to count. You would just count points inside a piece. And I don't know what I should say for that notation. I guess people write a dx sometimes for that. Maybe I should say dc. I've never thought about that. I should put dc to indicate that the way that you're going to measure the size of a piece of your zero-dimensional set is just to count the parts, count the points that are in that part. All right, so we've done different kinds of integrals over these different types of sets. The surface integrals, for example, well, the three-dimensional integrals, those were just a lot of Fubini's theorem. These two-dimensional integrals might have been Fubini's theorem if your surface was a chunk of the plane, but when we had our surface integrals on surfaces that were floating in three-dimensional space like this, well, then we had these little, we had to parameterize and find the fudge factors for stretching areas and all that stuff. And it got a little bit worse when we started to talk about the surface integrals that came from a vector field. Then you not only had to parameterize and chop up, but you had to figure out what exactly was the function, the scalar valued function that you were going to evaluate at each point. Same thing over here. We talked about different types of one-dimensional integrals, the Calc 1 integrals, the path integrals, and the line integrals. Today I want to tell you about a zero-dimensional integral. What is a zero-dimensional integral? If you have a finite set, oh, I don't know, let's just call the points A, B, and C, and somebody gives you a function that's defined on that set and says to please integrate that function over that set, I mean, what would you do? You divide this set into pieces, and you evaluate the function on each one of those pieces, and then you multiply by the count of the number of points in your piece. So you could just say it's, I'll just take the whole set. There's three points in there, and I evaluate the function at one of those points. Or you might say, no, 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 I'll get a better approximation to whatever it is I was really trying to compute by splitting this thing up more finely, break it into smaller pieces. So you might evaluate it, you might split it this way, and then say, well, there's f of a, and then the other piece has got a count of 2, and I evaluate that function at one of the points inside that piece. Or you could decide to break it up even into a finer division, and then of course you're just adding up the values of the function at each one of those points. So integrating a zero-dimensional integral just means you take your function and you just keep evaluating it at every point and just add them up. So it's still the same spirit as what all of our other integrals have meant, except we didn't need to talk about the size of our set in any other way besides just counting the points in there. So that seems like a dumb thing to do, but hey, why not? Let's put this idea of just adding up values of a function. We'll use this integral notation. Now, I did say we had different kinds of one-dimensional integrals, and in particular, when we got to integrals over curves and started talking about the line integral, we realized that, you know, sometimes you need to take your curve and decide which direction you're moving on. Not in order to evaluate the path integral, but in order to evaluate the line integral that somehow came from a force field or a vector field. You know, the amount of work needed to go that way is the negative of the amount needed to go that way. So we did start to talk about picking an orientation. And if you pick the opposite orientation, there's nothing like wrong with that, but you'll be just getting the negative of the previous integral. And that might apply to a one-dimensional set that happened to be the union of a couple of curves. If somebody gives you a one-dimensional set like this and says, please compute an integral over that, you have to decide which way you want to parameterize each one of those parts. There's nothing like wrong with doing one of the orientations instead of the other one, but you do need to decide that, well, yes, I'm going to compute it in one order or the other, and then after I do that computation, I might need to add one of them and subtract the other one, because for whatever reason, the way I did my computation was backwards from the way the little arrow was drawn. And the same thing happened for surface integrals. In order to compute the surface integrals that came from a vector field, one of the things you had to assess before you started doing any integration was, hey, which way are we going to pick the unit normal at each point? Because choosing the opposite one would just give us the negative of the integral. And so if you have a two-dimensional set that happens to be the disjoint union of a couple of sections of a surface, well, you could compute them using whatever orientation you want, but then you have to compare that to the problem as it was given, and the problem might have said, yeah, I actually wanted you to add this one and subtract that one. When I look at the unit normals you've just drawn, this one matches my application and this one is opposite my application. So please add this integral and then subtract that integral. Okay, we haven't had to do examples where we had disjoint curves or disjoint surfaces, but we have noticed that sometimes you need to negate something because for the application you have in mind, the little vectors that you're drawing, the unit vectors, they either match the application or they don't. The reason that I go through all that is because even in zero-dimensional integrals, it makes sense to add up all these values in some cases, but maybe depending on your application, you might want to be subtracting some of them. So in other words, you need to look at these points inside your finite set and assign each one of them either a plus sign or a minus sign, depending on your application. And you say, yeah, when I write this zero-dimensional integral, what I mean is for you to take the values of the functions and the values of the function and add some of them and subtract the others. Now, this seems like an awful lot of work to just say, please add some of the values of the function and subtract some of the other ones. But the reason that I do all of this, everything that I've done here, is just to show you that a theorem that you already know can be written in a way that matches the other theorems we're going to have in Chapter 8. So here's the theorem you already know. It's the fundamental theorem of calculus. And there's a couple of versions that you know of this one. One of the forms says you could take any function that you like and integrate it, let's say with respect to t, as t ranges from a up to a moving right-hand endpoint. Then the value of this integral, I mean, yeah, it's a number, but it's a number that depends on x. It's, you know, the area under a curve or whatever. So this is a function of x, and you know that when you differentiate that function of x, what you get is the same function that you started with. I mean, it's a function of x now, not t, but that's one way that you have been given the fundamental theorem of calculus. Another way that it has been written for you is to say, you know, if you wanted to integrate a function from a to b, it sure would be handy if that function happened to be the derivative of something else. In other words, you look at your integrand and you say, huh, can I anti-differentiate this function? Can I think of a function capital F whose derivative is the little f that I was given in the first place? Because if I can, then computing this integral is a snap. You just take that antiderivative and you evaluate it at b and at a and subtract. Oh, look at that. That's exactly the kind of thing that today I am calling a zero-dimensional integral of the function capital F. You can write it as, you can put f of x, I guess, if you like. But anyway, it's the function capital F. Your measure of size here is just a count. And that's because you have only a finite zero-dimensional set to integrate over. You're just integrating over the set that contains only a and b. And apparently, according to the fundamental theorem of calculus, I can make it match what I've talked about before if I remember to give the number b the positive sign and the number a gets the minus sign. So, the fundamental theorem of calculus can be written in this way. It says that when you want to compute the integral over some interval, if the function that you're integrating is a derivative of some other function, capital F, and then you're computing this one-dimensional integral. I'm switching to the letter L now to say that this was supposed to be a measurement of length, and that's one of the notations. This is the one I like better for our curves and other paths. I use dl instead of ds or dx. But anyway, if you're back in Calc 1, if you have a function capital F, if you differentiate it and then compute an integral with respect to length over some interval, and you guys all know the picture, right? You've got all those little towering rectangles nestled next to each other. Then this can be written as the zero-dimensional integral of the function that you were differentiating on this side, and the zero-dimensional set that you're integrating over on this side is the boundary of the interval. As a set, it's just the two endpoints, but specifically, you take those two endpoints and you assign a positive sign to the right-hand endpoint and a negative sign to the left-hand endpoint. So you've never written it this way before. There's no real reason you should write it, but this is the fundamental theorem of calculus in the notation that we're going to see in Chapter 8. It's a little informal here, but the spirit of it is that the fundamental theorem of calculus asserts that two integrals are equal to each other. One of the integrals can be over an arbitrary interval in the real number line, and then in that case, the other integral is just over its boundary. One of the integrals can use any function of one variable, and then the function that shows up on the other side is a derivative of that function, capital F. One of them is a one-dimensional integral, so our measurement of size is a length, and the other is a zero-dimensional integral, so our notion of size is just a count. So it's two different integrals. there's something similar on each side. There's always the region of integration, there's the function being integrated, and there's the measurement of your notion of size, and they have to change. But in every case, there's some sort of natural connection between the decision you make on the left and the decision you make on the right. That is the spirit in which we're going to have all the other theorems of chapter 8. They're all going to say that two integrals are equal. They will be integrals over different dimensions. This has got a zero-dimensional integral on the right and a one-dimensional integral on the left. The next example we're going to do will have a one-dimensional integral on the right and a two-dimensional integral on the left. But it'll be the same spirit. You'll have some arbitrary thingy to integrate on the lower dimension, and what you're integrating on the right-hand side, on the other side, will be some sort of derivative of that. Over here, you can have an arbitrary region, an arbitrary two-dimensional region, but what will show up over here will be the boundary of that region. So that's the one we're going to do today. Green's theorem, it's called. And then there's also things called Stokes' theorem and Gauss's theorem that will keep the same spirit moving in different versions of the different integrals that we've talked about. Cool? Comments on that? Any comments on the fundamental game of calculus? Let's make sure we're all familiar with that. All right. So, bear with me now as I write down Green's theorem. This is due to Green, George Green, what's his name? And the setting in this case is, as I said, it's going to be not zero and one-dimensional, but one-dimensional on one side and two-dimensional on the other side. And so what am I doing with the two dimensions? What I'm going to have is let S be any, well, really any reasonable bounded subset of the plane. You remember what the word bounded means. It just means you can put the whole thing inside a big old circle. I don't want you to use S to be a quadrant of the plane or something like that. So that's going to be the region of integration on the left-hand side. What goes on the right-hand side is going to be the boundary of this set S, and I'm going to use this notation for that. You'll see me use this notation all the time in chapter 8, that it's the partial derivative symbol just all by itself, but it's not attached to a function, it's attached to a set. And it means, literally it means the boundary of the set S, with a little caveat that I'm going to have to tell you about, a little interpretation question that we're going to have to get to as soon as I finish the rest of the statement of the theorem. So I'll be, on the left-hand side here, I'll be integrating over the set S, and on the right-hand side, I'll be integrating over the boundary of S. Now, how about my integrand? The one-dimensional integrals that we're going to have on the right-hand side of Green's theorem will be line integrals. So those are the ones that come from a vector field. So suppose that I have a vector field that's got two components, a vector field in the plane. So I'll use this notation I'll use P and Q as the names of the functions that come before and after the comma. But at every point in the plane, this is supposed to give you a vector in the plane. X's and Y's go in and a vector comes out. So this you can think of this as being a vector field. I'll just draw pictures with you that have a lot of little arrows. Now I referred over here to asking you to take some kind of a derivative of the thing that showed up on the right-hand side. Specifically, what I'm going to ask you to look at is the following function of x and y. Take the function q of x and y and take its partial with respect to x. Then take the function p, that's also a function of x and y, but differentiate that one with respect to y and subtract. All right, with all of this symbolism in here, then here's Green's theorem. I should have said if, not let. How's that? If you have all this stuff lined up, then Green says that a two-dimensional integral, the integral of the function little f that I've just computed here, integrated over the two-dimensional subset of the plane that you started with, will match the value of the line integral over the boundary of S of the following quantity. So line integrals, we have different notations for those. I'm going to have to remind you of those today. But one of the ways that we write them is we write out the first function with a dx after it and the second function with the dy after it. So that's it. That's what Green's theorem says. It says that two integrals are equal. This one's a one-dimensional integral. This is a two-dimensional integral. So it will feel in some sense like the fundamental theorem of calculus. Now I have to tell you before I do anything else, you guys all walked away from the fundamental theorem of calculus thinking that the way you're always going to use this is that this is the thing you're given and somebody asks you to evaluate an integral. And the way you handle that is you look at your integrand, you try to figure out what the heck that function is the derivative of. In other words, you anti-differentiate. And then going over here, you say, oh, well, this one is easy. I just plug in some endpoints and subtract. So you've always gone from left to right. And there was some difficulty, actually, in trying to figure out how do you get an antiderivative of a function. That was all of Calc 2. In Green's theorem, the same thing might be true. You might be looking at this integral, and you are trying to figure out how the heck you're going to compute an integral of some function of two variables over a chunk of the two-dimensional plane. Green's theorem allows you to rewrite that as a line integral. But probably for a lot of you guys, this left-hand side, in general, that probably feels easier because you just use Fubini's theorem to evaluate this kind of a thing. Whereas the line integrals, I know a bunch of you guys don't like that because you have to start parameterizing curves. And so you might be tempted to go that way. And Green's theorem says, doesn't matter. You can go either way you want. The theorem merely asserts that these two integrals are equal. So in practice, you see both kinds of applications. Sometimes this is the hard one and you change it to this, which is easy, and sometimes this is the easy one, the hard one, and you make that one easier. So I'm going to give you some applications. I don't know if I'm going to be able to get too far with them today, but we'll continue with this on Monday. But before we do any applications, I got to make sure you understand what all this stuff is saying. So just to draw you a kind of a general picture, the way Green's theorem is stated, you have to begin with a subset like this. So some sort of a chunk of two-dimensional space. Then the boundary of S is this curve here. And the integral on the left is the one that says, well, whatever this function turns out to be, if you simply chop this region up into a lot of little pieces, you evaluate this function at each one of these pieces and multiply by the size of that little piece, the area of that piece. Okay, that's how you get the numerical value over here. This one, this is the one that says that P and Q together are defining a vector field. So there's, some vector field defined at all points in the plane. And in particular, it's defined at various points along this curve. And, well, when you compute a line integral, one of the interpretations here is that you're calculating the work that you would do, or the work that's done on you, depending on your interpretation. As you walk along the curve, so you take the size of the vector field, the magnitude of that vector field, but you reduce it by the cosine of this angle that's in here. So in a case like this, the direction you're moving in is almost the same as the direction of the vector field, and so the contribution at this point is almost equal to the magnitude of that vector field. Whereas in this case, it appears that you're kind of walking opposite from the way the vector field is pointing. So the dot product of f with this unit vector would actually be a negative number. So you're subtracting something here. And in this case, it's the dot product would be 0. All right, so that's what this right-hand side is computing. Now, as I say that, one of the things that you should remember is if you should decide to parameterize the curve the other way, then you'll pick up a minus sign from the value of the integral. You'll replace the integral with its negative. That's because the interpretation is that it's no longer you doing work to fight the force, but rather the force is doing work on you to push you around. So you do have to pick an orientation of this curve, a direction of travel on the curve that matches whatever your application is. The mathematician in us doesn't really care which way you choose the orientation. Just you figure that out based on what your application is for the line integral. Okay, well, in this setting, it's not clear that there is an application. So how do we know which one of these two orientations to pick? Because after all, they can't both be equal to this. I mean, unless everything is equal to 0. And there is an answer. The answer is that Green's theorem is going to give you the right integral, but only if you take this boundary and you traverse it counterclockwise. So that was the extra little caveat that I said I was going to have to add in here. The boundary has to be traversed counterclockwise, which is the way I did it, because I've done this so many times in my life. I already drew it counterclockwise, but you have to remember to do likewise. You have to remember in your parameterization, you know, to compute this line integral, you would actually have to parameterize the curve, so you have to choose a parameterization that is consistent with the direction that Green's theorem requires. Okay, so this is the kind of picture that you will always have in an application of Green's theorem. What will vary, of course, is exactly what's the vector field and what exactly is the set S that you're integrating over. But the interpretations of the two sides, you know, you guys know what those are. All right, so if you're ready now, I'm going to show you an example to just calculate the two integrals on the two sides so that you can see what we're going to do. And I really don't have to be very special about the P and the Q. I'll choose some random things there, but to make it an easy example, I want to choose S to be a very simple set. So let's choose S to be a rectangle that's lined up with the axes. So we've discussed this kind of thing before. Here's a notation that we use for this. This is called taking a Cartesian product of two intervals. So that means it's the region in the plane where the x coordinates can be any numbers between A and B. And independently of what your x coordinate is, your y coordinate can be any number between C and D. So the x's come from this interval, the y's come from that interval, and then the pairs, x comma y, they come from this set. There's the set S in the xy plane. And let's have a vector field. I really don't care. Let's have it be something like, I don't know, x squared y cubed. And then here I'll put 3x plus 4y. So I don't even know what this vector field would look like. You can go calculate the values of this vector for the different combinations of x's and y's. I mean, I guess I get the 0 vector right at the origin. And along the horizontal axis, along either axis, this vector field points vertically, but I don't know how big the arrows should be. And then the rest of I really only know how the vector field behaves around the boundary, but I don't know what picture to draw. I'll let you experiment with that. So let's calculate what we're going to get when we address the two sides of Green's theorem. There's no rule that says one of them is supposed to be the left side and the other is called the right-hand side, but let's try to be consistent here. So with this notation here, my left-hand side is a two-dimensional integral. The function I'm supposed to be integrating it's the partial of q with respect to x minus the partial of p with respect to y. And I'll compute a surface integral, an area integral of that function over this rectangle. So of course I have to first compute this integrand. So the partial of the second one with respect to x is 3, and the partial of the first one with respect to y is 3x squared y squared. And I need to compute an area integral of that. But, you know, this is a rectangle, so why don't I just use Fubini's theorem? Fubini lets me write this as an iteration of two one-dimensional integrals. I could have the x coordinates go from A to B, and the y coordinates go from C to D. And my function then has to be integrated with respect to, well, I've got y on the inside and x on the outside. So here I go. I got to start, well, I'm actually going to use the fundamental theorem of calculus. That's true in general. These theorems that are a generalization of the fundamental theorem of calculus, they actually kind of build on that theorem. Because in order to evaluate this integral with respect to y, I need an antiderivative with respect to y. And for the first part, I'm just going to write 3y. But for the second part, you know, computing this antiderivative with respect to y, at some point, I actually differentiated this one with respect to y. So you see I'm sort of undoing some of the work that I used to write this integrand. That's why this is a generalization of the fundamental theorem of calculus. Anyway, don't worry about that too much. I anti-differentiate it with respect to y, and I stick in these two endpoints, these two values of y, and that'll be what I differentiate with respect to x. So then I'll be just integrating a function of just one variable x between two limits. My integrand is going to be 3 times, I'll have a d and a c subtracted, and then there's going to be x squared times d squared minus c squared. And I got to integrate that with respect to x. This is not supposed to be exciting, but I do want to have the answer finally written down. So here's this constant that you're integrating over an interval. You just multiply the constant by the length of the interval. As for this one, the antiderivative would be x cubed times that constant. So when I stick in these two endpoints, I'll get this constant times b cubed minus a cubed over 3. All right, so yada, 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 nothing of consequence. But we will compare that now to the formula that I will get on the other side. If I can find a better marker. How's this one? Okay, we'll try this. All right, so the thing that I called the right-hand side was a line integral. So this is supposed to be the integral around the boundary of the set S, and it has to be parameterized counterclockwise. And the line integral has been written this way. It's p dx plus q dy. So in our example, that's x squared times y cubed. You can see the p and q still up here. That times dx plus this times dy. Now, this is only one of the ways that we write out line integrals. I do want you guys to feel comfortable seeing this. I also want you to find a notation that feels more intuitive for you. If I can just abbreviate these as p and q for a moment, like I did before. This is the same as integrating the dot product of the vector field p and q with this sort of vector differential that has dx as its first component and dy as the second component. This is the thing that the book tends to write as a vector ds. They use a little boldface for you. And then this would be the thing they call the vector field. Maybe they just use a single letter for capital F. Another way that they have written this is that you're computing the dot product of the vector field with the unit tangent vector. And that is now a scalar valued function that you can compute as a path integral. So this is the moment when we're going to have to make sure we choose the appropriate unit vector, unit tangent vector. You need the one that points in the direction that you're traversing around the curve. I guess those are the only notations that I need for today. But anyway, whichever those notations you need, you like, you have to be ready to use them to calculate this integral, this line integral, around the boundary of the set S. Now, my set S has become a rectangle in this example, and I'm supposed to go around it counterclockwise. So here is my curve. It's not a very curvy curve, but there is the curve over which I have to compute this line integral. It's the union of 4 separate line segments, but it's important to remember that these line segments are traversed in a certain direction. So my right-hand side then is it's supposed to be a single line integral around this rectangle, But the way you would compute it is to take the sum of 4 separate line integrals. In every case, you just compute the vector field dotted with the unit vector in your direction. So it becomes this path integral, and then I'll have to add those 4 path integrals together. And I'm not going to do all 4 of them. I certainly won't have time to finish that today. But let's do 2 of them. I just want to illustrate 2 of them for you. So how do we compute this first line integral? Well, you always need a parameterization that gets you along this path from this point to this point. Now, there's a couple of ways I could parameterize that. One way that I might do it on this first length is to say, well, here's where I want to be at time t. How about if I just go to the point t comma d? If you let t range over the interval from a to b, that means you'll start at a comma b, I'm sorry, this should be a c, because this is c and this was d. So you'll start at a comma c and you'll end at b comma c. Perfectly reasonable parameterization. You might also do it this way. You might say phi of t is, well, I'm going to start at the point a comma c, and then I know I have to move. I'm trying to parameterize a movement from one point to another point. One of the ways that we've talked about doing that is you just add in multiples, fractional multiples of the vector that joins that point to that point. And in our case, that vector is just b minus a comma 0. So here you just let t range from 0 to 1, and that will give you your parameterization. There's other parameterizations you could use too, of course. You always have infinitely many choices. But let's just pick one. Let me use this first parameterization. So in order to evaluate this integral then, I need to take the dot product of capital F with the unit vector that's going in my direction. Well, okay, so where was that vector field? Here, 3x squared, blah, blah, blah. So if this is the vector field, there's the p and the q. And here's where I'm going to be at time t. This will be my x coordinate, that'll be my y coordinate, and so the value of the vector field is t squared c cubed, comma, 3t plus 4c. And I now have to take the dot product of that with the unit vector that points in my direction. Well, shoot, for curve C1, the unit vector is just the vector that points straight east. It's the one we've called I. It's this vector. And that's the thing you want to compute as a, sorry, I'm going to integrate that with respect to t as t goes from a to b. Well, fortunately, this dot product gets nice and easy because of that factor of a 0. So now you're just computing the integral of t squared c cubed dt between t equals a and t equals b. The antiderivative is t cubed over 3. I stick in the endpoints. I'm going to get c cubed times b cubed minus a cubed over 3. Easy. Also easy, apparently, but maybe not, will be the integral over C3. C3 looks just like C1. It's a set of points that have a fixed y coordinate. And so you might be tempted to use, for this part of the path integral, you might be tempted to use this parameterization. Phi of t is equal to not t comma c, but t comma d. And you just say, well, and all the t coordinates need to range between a and b. The problem with this is that as t runs over this interval, you start with the smaller number and you end up with the bigger number. So that's going to parameterize this path all right, but it'll go backwards. So you need to do something different. Now, if you are just on the ball and you can see which way your parameterization works, then you can use it. And then remember that as you compute the line integral with this parameterization, it's actually going to compute the negative of the thing you really want for this term. So, oops, sorry, that was an L. So, so go ahead and compute the integral using this parameterization if you want, but then take the negative of your answer at the end. Or, because I don't feel like that's exactly a convincing and very natural thing to do, you might try something like this. Why don't you recreate the idea that I had before that says, hey, we're going to start at the point b comma d, and move towards the point A comma D. So we'll add in fractional multiples of the vector that'll get us there. The vector that points from where we start to where we want to end up is this vector right here. So this would be a parameterization that I think would be a little bit safer for you. So sure, you get a bunch of points that have D as their final component. It has to be that way. But exactly how you're parameterizing the range of the x coordinates, that's a little different. If you choose this one, then how would you compute the integral? You know that one of the ways to compute a line integral is choose an arbitrary parameterization. You don't have to worry about the unit vector because of that little magic I talked about where nature gives you a gift and the factors that I call the speed, they ended up canceling. So my velocity vector is exactly this vector that I spoke of earlier, a minus b comma 0. And so all I need to do is to say, oh, and I should have said here, this parameterization uses values of t between 0 and 1. So this integral can be computed as the integral over the interval from 0 to 1 of, where's capital F? I lost it here. The vector field is t squared d cubed comma 3t plus 4d, and the vector is a minus b. That's what you integrate with respect to t, as t ranges over this interval. So again, the dot product is not so hard because of that 0 in there. You'll end up multiplying this by this. Integrate with respect to t, the antiderivative is t cubed over 3, but you are only plugging in t's between 0 and 1, and so you'll end up with 1/3 of d cubed times a minus b as your final integral. Wait, I did something wrong. T. Oh, I'm sorry. I was just copying the integral that I had last time and making little adjustments. I should have been putting x squared times y cubed. Here's the y, all right, but here is the x. So this quantity is what should have been squared. My bad. So that's the x that needs to get squared. So I apologize, that's actually not the value of the integral. I will tell you actually what you're going to get when you are done integrating it. You will get minus d cubed times b cubed minus a cubed over 3. And the minus sign is baked into the calculation. It comes out when I properly parameterize this curve. So I told you I was going to have to add up the line integrals over 4 separate paths. I jumped from C1 to C3, but these are the sums that I got for those first two. You had a c cubed times this stuff minus a d cubed times that stuff. Those two terms put together account for a good portion of what I computed for the other side of my integral. Look, there was a how do I get? My exponents are off. Somehow I messed up my exponents. Wow, and I'm really out of time here. I have to apologize. I don't know where I made a slip up in my calculation, but there's the two of the terms here. I mean, sorry, this end of the calculation that I did when I was addressing the left side of Green's theorem, that should be exactly the sum of the terms that I've computed so far on the right side. There's two other line integrals to compute on the right-hand side. Their sum should give you exactly this part. So I apologize. I've obviously made an arithmetic mistake somewhere, but trust me that does work. And what you just saw me do is typical of what would happen if somebody said, please verify Green's theorem. They want you to go take a picture just like this, where all the ingredients have been given, and on the one side, you're supposed to compute a surface integral over the set S, and on the other side, you compute line integral around the boundary oriented properly. So I want to continue this on Monday and do a lot more examples and applications, but I can't resist because it's going to be the weekend and I don't get to see you guys for several days. I have to tell you about a tool called a planimeter, and I invite you to go look. These are things you could actually buy, and I'll tell you what they do. Suppose that I asked you to compute the integral of minus 1/2 y dx plus 1/2 x dy. And I asked you to compute that integral around a closed curve in the xy plane in this direction. That's a line integral. You could compute it if you could parameterize the curve. Alternatively, you could use Green's theorem to say, oh, well, that's going to be the integral over the interior of this region. And what you're going to be integrating will be the partial of this with respect to y minus the partial of this with, sorry, the partial of this with respect to x minus the partial of this with respect to y. And that's just a 1. So you're computing the integral of 1 over the set that's shown. You are, in fact, computing the area of the set. This is very cool. You could, for example, grab a map, trace out the outline of Texas, and if you can compute the line integral as you go, it will tell you the area of Texas. You could have a little handheld device that if it can somehow magically compute line integrals as you go. I mean, it's not magic. You just need to keep evaluating the vector field and multiplying it by unit vectors. You can compute the area of the region you just surrounded. People have actually invented such a tool. It's called a planimeter. And you know, if you're a surveyor or a cartographer, you could actually use this to compute areas by merely tracing the outside. You're not computing the perimeter. The perimeter would be easy. You've probably seen surveyors that walk along with just this little wheel that's attached to a tape measure somehow. That would measure the perimeter. That's not what this is doing. There's a more complicated box in there somewhere that has to do the calculation of the line integral as you go. But at the end, when you come all the way back to where you started, it would report what the area is of the region you just walked around. So does it work like a GPS is the question, and the answer is no. You do not have to have, well, no, you don't have to have that. You just need to know the value of, you need to have a sense, well, I guess you do have to know your current coordinates as you compute the line integral. That would be the surveyor's one, but the handheld one doesn't need that. It just has to sense your x and y coordinates on a piece of graph paper as you go. And if it knows what your x and y coordinates were a moment ago, and it knows your x and y coordinates now, then it knows the vector that you just traversed. So that becomes the unit vector part of the calculation. It's very clever, and I don't want to get into the mechanics of it, but I'll tell you what it's doing is it's just computing this line integral. Anyway, I said I would do my applications on Monday, and we can return to this one on areas in particular, but there's other applications that we'll have too. Sometimes the left-hand side of Green's theorem is the easier one to compute. Sometimes it's the right-hand side. And this is a nice double-edged sword. All right, I'm going to stop here. We'll continue this discussion, and we have more theorems to go next week. They're all cool. So you can do some more of the homework problems now. Ask me about them on Monday. How's that? Oh, one more thing. I'm going to turn to my office hours now. I will have office hours here at 1 o'clock. At 3 o'clock, I have sometimes had Friday afternoon office hours, but I'm not going to do that today. I have to leave. All righty, guys. We'll see you on Monday.
Thanks, Dr. Russell.
Thank you.